All right, welcome to The Explainer. Today, we're digging into a 19th century experiment that, and I'm not exaggerating here, started with a simple ice bucket, but ended up protecting pretty much every piece of modern technology we all depend on.
You know that feeling, right? That little crackle of static when you pull off a sweater? It all starts with this invisible force, electric charge. Particles can push and pull on each other without ever touching, and figuring out how that works, well, that's where our story begins. The key idea here, the secret sauce, is something called electrostatic induction. And really, it's just the science behind static cling. It means you can take a charged object, bring it near something else, and from a distance, it forces the charges in that second object to separate, to rearrange themselves.
So picture this. You bring a positively charged rod near a neutral piece of metal. Now, that metal is jam-packed with electrons that are free to move around. And since opposites attract, those negative electrons get pulled toward the positive rod. They kind of shuffle over to one side. And what does that do? It leaves the other side of the metal with a positive charge. No touching required, it's all just influence, an invisible dance.
Okay, so you've got this invisible force. How in the world do you measure it? How do you control it? Well, back in the 1840s, this absolute genius, Michael Faraday, came up with a brilliant and, surprisingly simple device to do exactly that. He literally used a metal ice pail. And now it wasn't for keeping his drinks cold. He realized that its shape, this hollow, conductive container, was absolutely perfect. It was the ideal laboratory for figuring out how these induced charges actually behave. So how did this whole thing work? Well, Faraday's experiment is just beautiful in its simplicity. It reveals these fundamental rules about our universe in just a few super logical steps. Let's break it down.
So first, you take a charged object, let's say it's positive, and you lower it down into the pail. Super important, you don't let it touch the sides. And boom, the pail reacts instantly. Its own charges separate. It draws an equal amount of negative charge to its inner surface, almost like it's greeting the positive object inside. And in doing so, it pushes an equal amount of positive charge to its outer surface. And that outside charge, that's something Faraday could actually measure.
Now, the really crucial insight here isn't just what happens, but why it happens. See, those charges inside the metal walls of the pail, they keep shifting and rearranging themselves until the electric field inside the metal itself becomes zero. Everything's perfectly balanced. It reaches this calm state we call static equilibrium.
And this experiment also showed there were two different ways to charge the pail. The simple way was charging by contact. You just touch the charged object to the inside and poof, the charge transfers directly. But the clever way was using induction. While that positive object was held inside, Faraday could briefly touch the outside of the pail to the ground. That gave all those repelled positive charges an escape route. They'd flee, leaving the pail with a trapped net negative charge. Pretty cool trick.
Now this is where it gets really profound. That perfect one-to-one relationship, the fact that the charge on the outside of the pail exactly matched the charge of the object inside, that wasn't just some happy accident. No way. Faraday had stumbled upon a fundamental law of physics.
But think about it for a second. How does the pail know? It's not like it has a tiny calculator in there adding things up. How does it know the exact amount of charge to push to the outside? The answer is, well, it's just so elegant. It all comes down to an imaginary boundary.
Let's do a little thought experiment. Just picture an invisible bubble. Physicists call it a Gaussian surface, and imagine it sitting entirely inside the metal walls of the pail. Now here's a non-negotiable rule of physics. Because the pail is a conductor in equilibrium, the electric field anywhere inside the metal has to be zero. It just has to.
And that rule leads us to this huge idea called Gauss's law. You can think of it as the universe's accounting principle. It basically says, hey, if the electric field on the surface of your imaginary bubble is zero, then the total net electric charge inside that bubble also has to add up to zero. Period. The books have to balance perfectly.
So, think what that means. You put a positive charge inside our bubble. For the total to be zero, what is the pail forced to do? It has no choice. It has to pull an exactly equal amount of negative charge to its inner wall to cancel it out. And because charge can't just be created or destroyed, that means an equal amount of positive charge must get pushed to the outer wall. It's a perfect balancing act.
Okay, so this all might sound like a neat little 19th century lab trick, right? Wrong. This principle of separating and controlling electric fields is, well, it's an absolute cornerstone of the modern world.
What Faraday's ice pail really demonstrated is the idea of an electrostatic shield. It's like a two-way firewall for electricity. It can isolate whatever is inside from electric charges on the outside, and, just as importantly, it isolates the outside from whatever charges are placed inside it.
And this is the incredible legacy of that simple pail. We call this shielding principle a Faraday cage now. And it's everywhere. It's the metal mesh in your microwave door that keeps the waves in. It's the shielding that protects the sensitive electronics in your computer from getting fried. It's the entire room an MRI scanner sits in. It's even in the cables that bring you TV and internet.
0. That's the magic number. The value of the electric field inside any closed conductor in equilibrium is 0. That one simple concept, proven with an ice bucket, is what protects our electronics and makes so much of our technology possible today.
So from the static cling on your clothes, to an experiment with an ice bucket, to the technology in an MRI scanner that might one day save a life, it's all connected. It really makes you wonder, doesn't it? How many other profound, world-changing scientific principles are still out there, just hiding in plain sight?